The first section in the appendix, section A.1, is titled Radicals and Rational Exponents. And in this section, we're going to review how to simplify radical expressions, mainly square roots, cube roots. We'll also look at how to work with rational exponents, and we'll discover that rational exponents are just radical expressions, kind of in disguise. Well, first we'll start about as easy as I can make the problems, and that is we'll look at simply a number underneath a square root. So no variables yet, no cube roots, fourth roots, just simply square root of a number. And what you're looking for, what you're trying to do is answer the question, does this number here divide by a perfect square? If it does, we want to do that. We want to kind of set it up that way. So what we do is we rewrite the 120 as a product of two numbers. One of those two numbers is going to be the perfect square that divides into this number. And 120 happens to divide by 4. 4 times 30 is equal to 120. So I rewrite the 120 using a product of 4 times 30. The biggest key to simplifying these is one of these two numbers has to be a perfect square. Okay? If one of those two numbers is a perfect square, well then I can take the square root of this number and I can take that perfect square out. So the square root of 4 is 2. So we take that 4 outside the radical as a 2. And what's left behind is 2 times the square root of 30. Second example, let's look at the square root of 98. Same thing, can I divide 98 by a perfect square? Or can I rewrite 98 as a product of two numbers such that one of them is a perfect square? And we can. 98 is 49 times 2. 49 is a perfect square, so it comes out of the radical. The square root of 49 is what comes out. Square root of 49 is 7. So we end up with 7 times square root of 2. Well, so now what about a square root that has variables underneath them? Here we see this x to the 8th. Over here we see this x squared y cubed. How are we going to deal with those? Let me show the first example just by maybe splitting it up into two separate problems that we can then just put together in the end. Let's look at the 2 square root of 75, and let's look at the square root of x to the 8th. We can just put their answers back together at the end. Now with this one, it's just a number, so it's like the previous slide. We're just going to break it down into a product of two numbers. 75 is 25 times 3. 25 is a perfect square, so we take the square root. The square root of 25 is 5. Now since this 2 on the outside of the square root was originally multiplied to the square root, then it multiplies to whatever perfect square came out. So 5 times 2 makes 10. We have square root of 3 left over. Now the x to the 8th, there's two ways that I can look at the x to the 8th. I'll show you maybe breaking it down into perfect squares first. X to the 8th is x squared times x squared times x squared times x squared. Now each of these are perfect squares. They all come out. The square root of x squared is just x. So each of these brings out an x. Well, how many x's did I bring out? I brought out 4 x's. I brought out x to the 4th power. Notice that everything here came out, so there's nothing left behind in a radical here. So if I put this together, all the stuff that came out, I've got a 10x to the 4th. I've got a square root of 3 left behind. Second example, I'll go ahead and just do it maybe all at once this time. 18, I need two numbers that multiply to give 18. One of them has to be a perfect square, so we'll choose 9 times 2. I've got the x squared, it's already a perfect square. The y to the third is y squared times y. All the perfect squares come out. 9 comes out, x squared comes out, y squared comes out. And they come out again as their square roots. 9 comes out as 3, x squared comes out as x, y squared comes out as y. Underneath the square root we've got a 2 and a y left over. Now at the outset you would think that that is finished, and it's nearly finished. What I'm going to do is add one more thing to this. I'm going to add absolute value bars around the x and the y. The reason I add absolute value bars around the x and the y is because the variables must be positive. We know that we cannot take the square root of a negative number. Therefore, the principal root of the variable that came out, it's got to be a positive number. Since x or y respectively can represent both positive and negative numbers, I use the absolute value bars to force them to be positive. So now this is finished. Notice over here I did not use absolute value bars, and the reason why I didn't use them is because x to the fourth, or any number to the fourth power, is always going to result positive. So absolute value bars are not necessary in that case. So what about other kinds of radicals? Specifically cube roots, fourth roots. How do we deal with those? Well, we simply deal with them the same way as the square roots. I want two numbers that multiply to 54. One of those numbers has to be a perfect cube this time. Okay, so use a perfect cube this time. What do I mean by perfect cubes? Perfect cubes are 2 cubed, 3 cubed, 4 cubed, 5 cubed, etc. So I go kind of this way. 2 to the third power is 8. Can I do 8 times a number and get 54? I can't. So 3 to the third is 27. Can I do 27 times a number to get 54? And I can. So I'm going to use 27 times 2. 27 is the perfect cube. It comes out as 3. So the result is 3 cube root of 2. This next problem is a fourth root. So when I think about fourth roots, I have to use fourth powers. Like here I use third powers, I use perfect cubes. Here I'm going to use fourth powers. So I'm going to think of numbers like 2 to the fourth, 3 to the fourth, 4 to the fourth. These get big really fast, so you typically don't have to know very many of them, or you don't have to go very far. So let's see, this problem is 5 times the fourth root of 160, so I need two numbers that multiply to 160. One of those numbers should be one of these numbers. Well, it just so happens that our first one, 2 to the fourth power, is 16. 16 divides 160 10 times. So I use 16 times 10. 16 is the fourth powered number. The fourth root of 16 is 2. These numbers on the outside are going to multiply, so we get 10 fourth root of 10. A few more examples simplifying radicals, this time with variables underneath them. Fourth root. Well, I begin this problem, the way I begin any other problem is I break down the stuff underneath into fourth powers. Now it just so happens I can't break any of this down. The 3 is only 3 times 1, so it's just simply 3. X to the fourth is already a fourth power, and y to the second is smaller than a fourth power, so I can't break it down either. The only fourth power here is this x to the fourth, so it comes out as an x. So we've got x times the fourth root 3y squared. Now again, just like we saw a couple slides ago, I cannot take a square root of a negative number. I cannot take a fourth root of a negative number either. So I'm going to use absolute value bars around that variable. This next problem, cube root negative 24y to the sixth. Negative 24 would be negative 8 times 3. Y to the sixth would be y to the third times y to the third. I'm using thirds, third powers, because again this is a cube root, so I want perfect cubes under here. So let's underline my perfect cubes. It's negative 8, this y cubed, this y cubed. All of these perfect cubes come out. The things that aren't perfect cubes stay behind. Okay? So the cube root of negative 8 is negative 2. Cube root of y cubed is y. Cube root of y cubed is y. Cube root of 3 is left over. These two y's can multiply, so negative 2y squared times cube root of 3. Now real quick, notice that I didn't put absolute value bars around this variable like I did over here. A couple things about the absolute value bars. One, notice above on this cube root, I could cube root the negative number. It was a negative number itself. So when we're dealing with odd radicals, like cube roots and fifth roots, and if you happen to see seventh roots, since we can cube root, fifth root, etc., negative numbers, absolute value bars never are necessary. So absolute value is never needed with odd radicals. Okay, so cube roots, fifth roots, seventh roots, etc., on up. On the other hand, over here, with even radicals, okay, like fourth roots or square roots, etc. With even radicals, odd powers need absolute value bars. So notice this was x to the first, odd power needs absolute value bars. Whereas if it was x to the second, it would, by squaring it, would make it positive, it wouldn't need it. Of course, you could always put it there, so you could always just, anytime you see even radicals, just put absolute value bars on every variable. Sometimes it's just a little redundant.